modeling and analysis. I'm your host today, Deepak Shankar, and I'm the founder of Metabliss Design. Today, I'm going to go over some of the concepts of power management and power modeling in VisualSim. And before I do that, I want to just get over some of the logistics. You will see a control panel on the left-hand side. The control panel has a chat window. Feel free to type in any of your questions. There are a number of engineers standing by to answer any of your questions. One of the things I'm going to do is, this is our fourth stage in our training session and training webinar on VisualSim. Earlier, we completed some of the concepts of the basic block diagram editor, performance analysis, scheduling, software modeling. We're going to go over some of those, just repeat them quickly. And then we're going to go talk about power. We're going to talk all the way from end-to-end power, looking at generation, storage, consumption, and management. We're going to look at how it impacts at the system, subsystem, and chip level. And we're going to look at some of the reports and analysis that are output. And lastly, talk about hierarchical power analysis. This is a very new concept that we have introduced, and this is something that's going to make it extremely powerful for you to take advantage when you're designing your new designs, especially in places where you're building up IPs to put into chips, chips on boards, boards into an IoT, and then a network of these IoT systems. Quick overview. The VisualSim runs everything on a concept of data structures or transactions. So the data, the control, handshaking, logic, anything that flows through the model flows in the concept of a data structure. A data structure is similar to a C-like struct, which has a number of field names and associated values for it. Another concept in VisualSim is the logic or the RegEx. This is a series of functions that are available in VisualSim that accelerate your model construction, plus also accelerate the speed at which your simulation runs. So say you want to look up the depth of a cube, rather than going and writing logic to create it, we have a function called getBlockStatus. Similarly, we're going to see some in this presentation as well, where we talk about getting access to data, modifying certain attributes inside the power table and things like that also. The other aspect that we discussed is the selection of library blocks. VisualSim has over 300 library blocks. The question is, which library block fits into which aspect of your design? So if you're trying to do, say, a DMA design, or I'm trying to do real-time operating system design, or I'm doing a cache architecture, which library blocks do I select for that? Performance modeling is really about stochastic processes, which is you have certain activities that might consume certain amount of time, and there might be logic in between that might work on taking you to different routes within your particular system. Again, there we cover the aspect of library blocks and how do you select those. The last one was, the one we did last week was around software. One of the key aspects in VisualSim that we try to solve is the challenges faced by technologies such as SysML and AADL, which is the lack of a simulator and lack for the ability to be able to test your deadlines, your power consumption, your throughput, and other such as timing and power and functional requirements. We have a variety of schedulers, a variety of operating systems, and the ability for you to describe your software tasks. So these were some of the things we covered in the previous training classes. At the end of the session, we'll be sending you information and all the links for the videos associated with all of these different training sessions. So with that, let us move over to today's power analysis and power design in VisualSim. One of the key aspects in any of your architecture is energy. It could be right from consumption to management to how it impacts what your mechanical enclosure is going to be like. So you really want to get feedback very early in the design cycle to be able to identify where your limitations are or what you can really do with the space that is provided to you. So you can't have 200 watts of power on a USB dongle. So you have to have some expectation on what you can do with available power. You want to look at really end-to-end power, depending on what your design is. If you're doing like, say, a space system, you want to look at your photovoltaic cells, your batteries, all the way up to your management when you have an eclipse. The other aspect which is very, very important is your scalability. You have a system you built, you have certain applications, but what happens in the future when you want to add more applications? How does it impact your power? Most people today really look at what's the throughput I'm getting out of my processor, out of my bus. Is that sufficient when I put some more messages or I put some more data on the system? Really today is insufficient because your major cost in your data center is really your electricity bill. Your major design aspect in a IoT or a camera or any handheld device is the space available for you to be enabled the cooling. So really about trying to understand power at a very, very early stage in the design process. So what does VisualSim really provide you? There are really four aspects to it. The first thing is we provide you all the building blocks that are required to construct the system. Okay, it's your generation, your storage, your consumption, and your management logic. At this point, I'm going to go over to VisualSim, and we're going to take a look at a particular design. So what we have over here is the VisualSim architect. On the left-hand side, you see a series of libraries. So for example, I can drag and drop, say, the block here called the battery block. And what can happen is I can connect that up to any of the power table information, and I can have my power triggered into the battery block. Similarly, I have the power manager, which has all the power data. These are all the different devices in my system. And then right here, I'm going to go into some more details here, is the logic for your power management. So if I go in here, you can see it's got a significant amount of power data as well, or logic to figure out when you change your state. So this is something where you have your power battery. You can connect, say an energy harvester to connect that into this one here. You can have your power table, which manages all your consumption, which is all these different devices. And finally, you have your manager. So you really have an end-to-end power system that you can use to evaluate visuals. Now, what technologies that are available for you to be able to define your power data? The first and foremost is your power table. And in the power table, you can provide information such as, what is going to be the power in each state? What is the transition time between states? What is the expression for the power in each of the states? And, what is battery charging mode? All of this information can be incorporated into the different tables available in VisualSim. You already have a large number of predefined battery data. We're constantly working to add those so that we incorporate all the different types of batteries available. If there is a battery that you want, we can collect the data and include that in the system, update your system as well. So that is available also as part of the technology capability that we have. One of the key things in this technology is, as I showed you, that was this here was a hybrid electric vehicle system we're looking at. So you got like the different generators, you got your headlights, radio, radar, ECUs. Similarly, there's also power related, say, in the avionics place. There's a photovoltaic cell with a battery and all the different devices that are in my system, subsystems, and then the scheduler. Also have something that is more at the chip level, where I've got like PLL, clock, different states, and then the battery and an LDO. So you can see it can be incorporated at any level in the system exploration process. Also, as I just showed you, can be used for a variety of application spaces. So you're not restricted by saying, oh, I can only use this for, say, a modem, or I can only use this for, say, a camera. It can be really used across the spectrum for a wide variety of powers of applications. Now, why do you really need early system level power? One of the things we have seen among all our surveys is probably the biggest reason for system failure or product failure is really the amount of power, which is either in the terms of dissipation or in terms of battery life, or just very sluggish performance because the power drag that is required. The other aspect is your peak power consumption. A lot of times there might be spikes that are a result of like multiple things happening at the same time, which if used properly in a management process could be scaled with offsets so that spike never occurs. How does that help? You can reduce your your surges, which will in effect improve your battery life, improve the maximum power available for a longer period of time. Now, the other aspect is looking at all the different use cases and workload your systems will go through and try to understand what is going to be the battery life, what is going to be the power consumed, which will help me design what is going to be the capacity of the battery I need. And if I'm using a built-in charger, how big should the charger be? The other aspect which has caused a lot of handheld devices and a lot of space-based systems to fail is really the concept of overclocking the processor and the excessive power consumption that leads to a lot of these failures. So really understand where the power is being consumed in the system. Let's look at the basic concept in VisualSim for power technology. What you have here is, when you take any system, you have a series of functions and timing. These are the things that go to form the description of any particular design. The functionality can be related to some arbitration or logic, or it can be related to a mathematical algorithm, like say a finite FIR filter. The timing and resource is really about how many semaphores do I need on the software, how many partitions on my operating system, or how much of CPU bandwidth, or how much of the DMA is required. Those would get here on the timing. So when I look at just at a very coarse level, there's at least two states. There's an active state and an idle state. The active state is when these things are getting consumed. The idle state is when it's not getting consumed. And it's different for each device in your particular system. Now, as I keep going, feel free to ask any questions. Either I'll cover it during our presentation or one of my engineers will answer them as well. So, this is the basic concept of a system model and the basic concept of the power modes. Now, how does VisualSim Power Technology help? First and foremost is that it's really based on the activity, which is what is happening over here, and the logic to go from one state to another state. Now, within a particular state, you do have the power that's consumed. It can be that some of the newer generation process has different power levels for different tasks. So define those, but also any of the management logic to move from, say, a sleep state to a deep sleep state, or from a D1 to a D3. So allows you to cover that kind of information. Then of course you want to incorporate the hardware and software aspect, just like you are building a architecture model. And finally, what you want to look at is all the details, the four parts of a power system. Generation, which can be from a variety of systems or a variety of devices. Storage, which is different types of batteries. Consumption, which is, each one of these can have different resources, different timing, different data consumption, any of those things. And lastly, the management, which can be based on time. So if you're like 1 microsecond in sleep, move it over to D-sleep. Or if my system is in an eclipse, in a space-based system is in an eclipse, I better shut down most of my devices because I could go into cold store, which means I can never recover from it. So it can be more logic-based as well. The other one is generate power profiles for downstream testing. So, like for this use case, this is the type of power that is generated. So you can, downstream when you do the testing, like say in your verification process, you can validate, does that match what my system model is doing? So it becomes a golden reference. A variety of statistics that are generated by VisualSim for all 4 stages, which is the generation, storage, consumption, and management. So you can really now make power an integral part of your architecture exploration. Just every aspect of it becomes your architecture exploration. Let's start with the stage 1, which is your power generation. Now, there's a variety of building blocks in VisualSim regarding power generation. We have anything from photovoltaic, vibration, motion, pressure, air, solar, and even custom, where you can actually create your own proprietary technology. The key attributes are really the rate, how much charge is generated each time, what is the efficiency of that output, and what are the periods in which it's available. So for example, if I have solar, the solar might be available from 9 a.m. to 5 p.m., but the rest of the time may not be available at all. Wind energy can be available for variable quantity over the entire period of the day. So those are attributes that you can use to define your power generation. Now, one of the key things in VisualSim is you can also import a trace of your power profile, which is in an existing system, and use that to debug what is happening in your real design. So it allows you to import that as well. One of the key aspects we look at in VisualSim, which is one of the things that's plotted out of the battery, is really your input charge versus the consumed. A lot of times there's a lot more input coming in, but most of it is wasted because the charger has only certain capacity. So you could probably like adjust the amount of charge coming in by maybe going with a smaller photovoltaic cell or smaller motor generator, things like that. Now, looking at the parameters for the energy generation, this specific one is related to the time energy harvester. As I said, we've got other types as well, but this is the first one that we're looking at right now. Now, what are the things we have here? We got the maximum battery charge. We also have the, in this case, we're using a time-based. So this is a time period. And let's look at the solar thing. So we have from this time to this time, we have the efficiency, and that's the, from this starting watt hour to this ending watt hour, to the percentage of time. The period it's flat is about 50%. The period which is decline is 15, and then no activity is 20%. This can emulate your solar energy or solar power, and this can be used for that, to model a photovoltaic cell that can feed into a battery or into another storage system. So right here we got a steady charge as well, and we've got one which is more file-based. So you got a variety of these that are available to you for use in your particular system. Now, just by changing these parameters, you can create your own variation or your own definition of your system. Now, that was on generation. The generation feeds into the battery. One of the things we've got is, rather than user having to go in and search for the battery data, we've already collected battery data for a number of devices that are currently active in the market. Now, how does a battery fit into the rest of the system? It emulates the charge and discharge based on system requests. Think about your LDO going and getting data, going and getting power from your battery. That's in a sense how the battery model works. Now, today's battery models that you see would only give you, like your charge and your discharge. Our battery models go beyond that, where we look at what happens when you have external shocks and thermal activity. How does that impact the life of the battery? How does that impact the maximum charge? How many charge-discharge cycles do you have? At what rate do you charge-discharge? How many power surges, say over 50%? What is your discharge duty cycle? All of those impact your maximum charge and battery life, and that's incorporated into the VisualSim battery model. A variety of plots are generated from the system. So if you look at the parameters, notice we already have the list here, and you just simply select one of them, and that battery gets incorporated into your model. Variety of charging: the standard, custom, based on state of charge, and turbocharge. The turbocharge is kind of like your mobile charger, where initially, just to give you a bam of data, in about 15 minutes, 25–30% of the battery is already charged. But then to get the full charge, it still takes a significant amount of time as well. Now, these are some of the batteries that are available today, and we are constantly adding newer and newer batteries. So as you see, you will start seeing additional battery devices as well. Now, these are all the attributes that go in our system to define the battery. So, for the ID, what is the type of battery? What's the maximum voltage? What's the milliamp hours? What is the C rate that is used for your charging, and also for your discharge, the maximum discharge you can go. How many discharges in percentage age per month? So this is, what happens, there's always self-discharge when it's not being used, especially in like lithium-ion batteries. Maybe not there nickel hydride, but it's there in lithium-ion. So what is the discharge in per month? Number of charge cycles and associated reduction in age. When you have surge, what is the maximum surge, and what is the your loss as a result of your surge? Loss in terms of the battery life and in terms of the maximum power. Energy density, the charge hour. The charge hour here is what determines how quickly your battery gets charged in a standard charging mode. And then aging, just a standard aging process for your battery itself. Now, let's look at the custom charger. We've got the standard charge, which is based on your charge hours. So if it's 3.5 hours to charge, we know that's this amount of time, this is the amount of input rate that comes in. Based on that, we can determine, how quickly, how much a charge gets added at every second. Custom charge, when you turn on, you have a parameter to turn on custom charge. The 3 modes, or 2 modes, the first mode is based on state of charge. So we have want to go 50%. So battery drops, battery charge, immediate charge. The other one is discharge, which we have a table which provides you the what is the profile. Now let's look at a model that uses these battery chargers. So we got a very simple example. We've got energy harvester here that we're using, and in this case, the energy harvester we're using is just constant charge. Think about connected to a power outlet. Battery is a lithium ion, and we are doing custom charge. Charge, as soon as it drops, we just immediately start. And then we have a simple load here. We'll just put the load quickly. It's just using our scripting line to check an amount of traffic load here. So what are we doing here? Let's run the simulation. We get a variety of statistics that come out. Harvest, battery, and load. These are the statistics that we generate right out of the system. So let's look at some of those. This shows me the battery life remaining over time. This is based on all my thermal, my shocks, like my surges, aging, the duty cycle, all those attributes, come up to this one. This one tells me this is the maximum power available, but this was my instantaneous power that's actually being consumed based on the load of the system. So this shows me that I've got a battery that's like 3-watt battery, but I really need about 0.75. So I've really over-designed my battery, which immediately tells me that I've spent a lot of extra money that I could save right over here. Now, on this battery life remaining, one of the things you've got to be careful about is that the amount of Its remaining is actually dropped by a very small percentage. So in about 14,000, so about 14,000 seconds, this is the amount of loss in the battery life. We can now have also a scaling thing that tells you, what happens over a 10-year period. Now, this here, since we're using a custom battery charge, a custom battery charger, notice we drop the half and then we charge again. Drop the half, charge, drop the half, charge. So it's not a continuous charging process. The other aspect that you can see over here is the, so this is the input charge. That's the charge coming in from my harvester, which is a constant supply like the power strip. And this here, notice this was the increase over here, is the amount of power that's actually being used to charge the battery. This one here shows me what my peak energy is and what is the what is the available energy since the initial time, which is because of the battery aging process, the maximum power actually starts reducing. So you can see how much that reduction is. Now we do generate some statistics as well. So you can see what is the maximum load that was requested, and also when the battery is plugged on charge, what is the final battery life, the final battery capacity, what was the initial battery life, the max capacity, and then what was the reduction. So you can actually get a quick statistics on what it is that your battery is doing, and also what is it that you really need in terms of battery. This one here shows me the surges and shows me what is the power drop or the life drop as a result of that surges. So it gives me also like what are my failure modes in terms of how my system can actually collapse as well. So this is on the power itself, on the battery and on the consumption itself. Now, moving over from the battery charge and the battery consumption, the storage, we're going to move to the next aspect, which is, here's some of the reports I just showed you, so I'm going to skip these, is move over to the most important central aspect of our system, which is the power table. The power table itself manages all the state power information, which is, at every state, how much is the power consumed, cycles for the inductance. We assume there's no power losses under capacitance, so we don't take that into consideration. And the state change logic, which is how much time should I be in a state move over to another state. So that's the basic information that's made. How does the power table work? All the different devices in my system, be it processors, memories, buses, interfaces, any custom hardware, FPGAs, motherboards, like subsystems, like cameras, things like that. All of them are constantly consuming power, and those requests are actually handed over to the power table, which maintains all the information on how much of power is being consumed by the device. Everything is time-based, so you can actually see what is happening over time, not just at a particular instance in time. As I said, handles the transition time between states. It also outputs the power data for the battery to be able to manage the amount of power that is being consumed, looking at all the surges and all those aspects for the battery as well. These are the list of statistics that are generated out of the power table. So if I move back into VisualSim, actually, before I do that, I'm going to go over some more details, which is really about the power table block. If you look at the parameters for the power table block, one thing you can see, the first is the manager setup. So this maintains the list of all the devices in that particular power table. What are all the different types of states, and any number of states here. This one maintains what is the name of the active and what's the name of the inactive state. Because you can have multiple active states here, and there can be active and inactive based on the type of task that's being fed in. Existing is it gives you a profile of what is the current state. Now this has two uses. One is your initial state can be set here. The second thing that it can be used for is really about the, but if you're building a fully custom model, this would be the state you would keep changing every time there's a state change in your custom block as well. Now, these can be your state transition times. So this is your inductance associated with each of the states. You can, notice all of these, you can either have an expression, which can be computed right here in the expression list, or it can just be a value. We can have both of those as supported. You can have any number of parameters here, speed, voltage, LDO efficiency, any attribute here. And those again can be used in the expression. Now this one here shows me, for this particular device, if I'm in active 1, how much time should I be before I move to active 2? So this is more of a state-based logic that you can set up in your system. Now the assumption here is active 1 and active 2 are states in the model. Now, power management. Before we go into power management, let's look at a model that incorporates the power here. To do that, I'm actually going to pick a fairly simple model. And the reason I picked a simple model is because it's easy to explain. What we have over here is we got some traffic generators that are feeding into these different devices that are over here. And I've got my power table where I'm maintaining all my power information. Notice I have no state change thing because I'm only worried about active and standby. So one of the things you can see over here is these are my expressions associated with for these different states. Notice this one uses one of these parameters here. This one doesn't. This one just has a single value. So now when I go, and then of course you can have different types of units here to select which one you're going to be going towards. I'm going to go ahead and run the simulation. And what you see is this is the power output, and this is the instantaneous and the average power. So one of the things we talked about earlier on, which is notice here, you have these spikes. Most of the power is at this level. You have these spikes. So what happens? Your enclosure, your heat dissipation, everything has to be designed to this level. If you can do some shifts, you can drop that right down here. So let's look at a slightly more complex design. So we're going to look at this system over here where we got 4 different tasks or 4 different activities. We got a multi-core architecture here. And one of the things I have here is a shift, an offset. Why do we need the offset? We can look at initially, I have 4 cores. I'm going to go ahead and run the simulation. Notice over here, all my 4 cores are related to the 4 colors over here, the black, green, blue, and red. So if I go into any of these sections over here, notice all my devices are turned on at the same time. They all get completed at different times, and then they're inactive for an extended period of time. But all my 4 cores are active. Now, notice that I've got these peaks on my instant power, which is right here, but most of my power is within this range, 0.55 or 0.5 to 0.75. So is there a way I can eliminate some of these at 1? So one of the things I can do is I can start off by creating an offset. So rather than all the tasks arriving at the same time, they get offset a little bit. It's not a huge amount, but it's in milliseconds, but we're still going to try it out. So right here, one of the things you notice, only the blue and the black process, only 2 of the cores are really active. The rest of them are completely inactive, which means I really need a 2-core system. Here's the other aspect though. I was at 1, I'm at now 0.75. So I actually reduced the power consumption, my peak power consumption by almost, 25%, which is a huge in terms of cost saving for the rest of the system. Now, the other things I can do is, for example, I can do more of a dynamic scaling. So, I can alter the power over time. When I do that, you can see how the power consumption changes over time if I use different clock speeds and different clock rates. And how does that impact the latency? So while we've been only talking about the power, the latency, the utilization, the throughputs are really a major decisions. They're the ones that really determine how a consumer is going to use a product. But the power determines some of the key aspects that people are looking at today. What is the battery life on my phone? What is the capacity of my battery in terms of size? Things like that. So when I have a dynamic, first I have a dynamic voltage frequency scaling. The second thing is, I can look at various ways to modify the power, and then I see how it impacts my my system latency. So that's how the power table gets defined in these systems. The last aspect of it, we learned about generation, storage, consumption, and now management. Power management can be done using a variety of processes. So the basic one is already incorporated in the power table we saw here, which is, what is the time, how much time can it be in a particular state before it moves over to the next state. That is one. The other one is you can use a finite state machine, a script, or a trace file to be able to describe exactly what the power management is. An example of a power management is I can shut down a complete CAN network when there's no activity on it. Or for example, if a particular partition in my operating system is not active, which means there's no tasks there, you can just shut it down to bring it down to a sleep state, which means that I can definitely reduce the power during that particular state when nothing is being used. Another aspect of the trace file is something where I can import a trace from an existing system, create a model of that, and figure out where my system bottleneck is that's causing those power spikes. The other aspect is really looking at the requirements. How much is the power requirements for my particular system? Now, before I proceed, I know people have been trying to ask questions, but just want to remind you that we have this panel on the right-hand side where you can actually enter in the chat window, you can enter in your questions, and there are people waiting by to answer the questions. Now, these algorithms, you can actually do it as a software level algorithm, or you can do it at a hardware level algorithm, or it can be at the operating system level. So you can actually incorporate all of those into your particular design as well. Here's an example of something that's a more finite state machine, but you can have other types of algorithms as well. So I'm just going to move over to VisualSim. We're going to open up another model, which is doing power state-based analysis more at the software level. So here what I have is I've got all the work stats and the command station, the power information. These get triggered into the state machine, and depending on which activity, whether it's my communications, sensors, sonar, motor, cameras, it will trigger some of those in the robot, but at the same time it will also trigger the software. So I can vary how that software is executed, what is the logic associated with the software, to really be able to so here's one of the things. If you get an error message, instantly you can know exactly what the error was. So that way you can figure out what is happening in my particular system. So I generated this model, I tried to run it, but I ended up getting an error here. So it allows me to be able to figure out what these errors are, and I can fix these errors quickly. So it's part of the tool is also these generation of these errors as well. Reports. As I said, variety of reports. You get instantaneous, you get for total discharge, but you can also get power on each device and also per state within the device. So for example, I'm going to move over to one of my models that are there currently. So this is at the top level power, or my lowest level power. As you can see, it gives me information as to what is my expression. This tells me which one. So it's in the rack, and it's got the power manager there. You can see this is the data that we input into the model, and this is the power for each one of them. So for the rack, for the bus, and for the DRAM, you can see what the cumulative, standby, and active is for each one, and what's the total for the whole system. At the same time, I can also get the power for all the devices below that. It's a process called hierarchical power analysis. So for example, I can be at the top level of the IoT. I can have a power table for the board. I can have the power table for the chips, and then I can have the power information at an IP level. So one of the key questions that comes up is, I've got an IoT system that's got both wired and wireless structures. Can I apply this power modeling to that kind of a power system? Absolutely. So there's a lot of examples in VisualSim that center around wired and wireless cores. So you could actually describe the logic for wireless and wired cores in VisualSim using our building blocks. And then you can utilize that information to be able to simulate the model and then see what the power changes. So for example, say you have a Bluetooth device. You can, for example, look at what happens when I do a broad advertise versus a narrow advertise. What happens when I do a transmit versus receive? What happens when I go from sleep to advertise? What is the change in power? You can look at those. The other aspect you can look at in a wired system is you can look at, for example, if I have certain types of data, HTML versus voice over IP, how much is the power consumed? So you can look at an application-based power as well. Hopefully I answered your question. If you have more, feel free to ask them in the system on the right-hand side. I'm just going to give a few seconds. I know people have been typing questions. So give a few seconds for anyone that has any questions. The other question that came up right now is about a network. So one of the things that we have in VisualSim, where I find a model associated with that, which I believe I don't have a model on my machine. Let me check to see if I have a model. I don't have a model on my machine, but yes, you can actually look at the end-to-end power, which means IoT device going across a set of core routers to an edge router to the server and into the entire data center. So you can actually look at the end-to-end power consumption as well. Now, yes, you can actually look at a specific core. So a core can be made up of a bunch of IP blocks. So you can look at the power consumed by each of the individual IP blocks and also by the whole core as well that goes into a chip. So you can actually get individual. We have a concept here. I'm just going to open up a model here where this one is not really a processor. I'm sorry, not really a wired or wireless core, but just gives you an idea. So I have a top level, which has, go into that. And this has a particular set of devices. And I've got a power table for just this level. Now, when I go deeper into this level, go to the next level below it, which is called the next hierarchical level, I got another power table for that level. Similarly, I can go inside of this, which is a single core. I've got another power table right there. So, and then of course, when I can go back again inside of this again, and then again I have another power table at that level. So each level or each device can actually have its own power table. And then the top level will actually consolidate all of those and also connect to the battery. So you can have multiple batteries. So say you have 20 IoT devices. Each of them can be connected to a battery. And then at the top level of that device, and then it actually accumulates power for all the devices that are in its entire hierarchy of power devices or different levels within the chip for that system. So yes, you can actually look at the very granular detail of power consumption. I'm going to again give a few minutes because I know some more people are typing questions. You can actually respond if you have any additional questions or you feel the questions have been answered. Now, one thing about power, as I mentioned, you can get an end-to-end power of the whole network. So I've got 20 of these IoT devices, 6 hubs. I've got like core routers, everything in a data center. I can actually get the power for the entire system, not just for one device, but for all of them. Some of them can be attached to batteries. Some of them can be attached to the power strip on the wall socket. So you can actually have a mixture of these profiles as well. Now, we also have some designs where people are using piezoelectric type power generation for some of their IoT devices, so you can model those as well for your power. Custom power operations. So what we're talking about is more of the mainstream power. So you have an activity, during that time there's power consumed. You have the inactivity, it goes to standby, and then from there it may go to sleep or wait or deep sleep, any of the different states. Now, one of the things in VisualSim in the power table is you can have any number of states, 30 states, 60, 90, however states you want each of the devices. So these can be modified by having, saying, task 1 can use active 1, task 2 can use active 2. So you can actually, by task, change which active state needs to be utilized. Now, each one of them can have a completely different expression in the expression list at the bottom. All you do is these 3 things: existing on and off state parameters in the manager setup. You modify those to figure out which is your current active state and which is your current state itself, or your present state. The other aspect is you can actually change the power level. So for example, I can change the LDO efficiency, which will change the amount of power consumed by a device. I could change the frequency of the voltage, and that can impact the power that is being consumed. Or at a system level, I can change the number of core threads, which can reduce my generation, which can also cause some of the devices to run slower, which means the power consumed can be a little slower in each of the states. So you can look at that impact as well at a full system level. I think there's a few more questions coming back. I'm going to stop and see if some of those I could answer right here. Now, power analysis and management for custom devices. So one of the key things is a lot of times we provide the device blocks. So we have about 100 or so different types of hardware and software devices that we provide. Now, some of those may not be insufficient. Say you have a fully custom one. You can actually create your own states, and then you can define the energy consumption for each of the states. We provide the reports output, but we also provide a battery model and any of the LDOs related to it. So you can actually have a fully custom, for example, here's the LV voltage, your switch leakage, all of that information can be incorporated into your power table and into the power states. Now, one of the things we talked about was how do we change the power over time? You can actually change the power levels. So you can modify something, go from this state to another state, or you can get the instantaneous power consumed. So this can tell you how much power is being consumed by a particular device at a particular time interval. What this allows you to do is allows you to get the to be able to track is any device going out of range, which means it's consuming an inordinate amount of power. This was something on an IoT device. We got a PV cell, we got a battery that is connected to a power management unit right here. You have the RF transmitter receivers, you have the sensors, any of the interfaces, and the other types of loads. So these are all the use cases. So one of the key things to be able to test these is really looking at the use cases. So what are the use cases that the system is going to operate on? The other aspect you're looking at is what is the workload that is being fed to it. And then of course the other aspects are looking at the PV capacity and things like that as well. So here you use cases in your workload that's actually triggering this entire system. At a chip level, this one is a chip with a large number of IP blocks. Top level you can see DRAM, flash, Amber, it's got an Amber AXI bus, a hardware accelerator, memory select. You have an ARMS core which has got all the caches and things like that. Another question that came up right now, which I thought was interesting, was can we change the routing table and look at the power consumption? Absolutely. Matter of fact, you can even do more cognitive radio type power modeling on routing tables like a MANE type protocol and see how the power consumption is done based on distance, based on the environment, all of those. You can increase the power levels, things like that also. So yep, you can look at it based on routing table. So this one here has multiple use scenarios that are running concurrently, and you can look at what is the power consumed by the entire hardware system. So here, for example, we've got, we're looking at the 4 tasks, and this was the instantaneous power, where they're all running at the exact same time. And this is when we have it all shifted. So you can see what the difference is. And you can see what the difference in the latency is as well. So you notice that when we shifted it, there's actually a slight increase in the latency. So it's not it's not a zero loss in terms of the latency. There is a slight increase in the latency, but only for a few of them. Most of them continue to remain at the same level. Look at that 0.1, most of them at that level, but there's a few of them that are overloading. So this tells me that there are, it's not just because I shift it, doesn't mean I won't have any impact. I still do have a small impact on my system. Doing analysis of the scheduling simulation, I can have, like a baseline where the peak power is say 6.15 milliwatts. The average is, going between 1.5 and 2.5. And these were the different levels of latency. So when I modified it, I can see, like where my power dropped. But notice the average is actually pretty flat between 1.4, 1.5, not a whole lot of difference. The latency has increased a little bit. It was like 0.12 and we had 0.1. I'm sorry, this is 0.065, not 0.65. This is 0.12. Notice I got up to 0.122. So there is a slight increase in the frequency, in the latency as well. Now, moving over to the tool itself. You can create very complex expressions. So this is the table, the series of expressions, as you can see, the clock, the voltage, the area, all of those can also be included into your regular system. Similarly, you can actually have designs I'm going to take a simple. So this one here, for example, what I have is I've got 2 workload generators that are fed to 1 and 2. And here what I have is I've got a whole network defining up in these 2 processes. I've got initial routing table based on my connectivity here, the distances and the speed. Now, what I also have is I've got some logic here where dynamically I remove a link and after some time I add a link. So I remove the link at 100 and I add the link back at 150. So let's, when we run the simulation, see what happens to the system. So notice here, when I added the link back at 150, there's actually an even distribution of load, but the latency actually went up. So one of the things that becomes counterintuitive here is that even though I added the link, my latency actually went up. Which tells me that maybe it's using an extra hop, an extra path as it flows through the system. So you can actually midway change the routing table and see what impact power and the performance of the system as well. Matter of fact, you can actually look at this profile over here. Like right after the link was broken, right after the link was brought back again. I believe it's between 3 and 5. So it's between, I think between node 3 and node 5. I believe, notice over here, there's no node 3 and node 5, which means there was no direct connectivity. You can see that even though I had an extra link, my latency actually went down because I ended up having like an extra path that it had to go through. Now, as I mentioned, we also have these MANET type cognitive video protocols that you can also model, and that way you can also look at it more dynamic changes, not just by link pair, but associated with where it's located and things like that also. Okay. So with that, I've looked at the entire end-to-end system, which is, I looked at the generation, the storage, the consumption, and the management. We looked at a few examples of how it's used. We looked at it in end-to-end networking aspects where you can see how the system behaves in its entirety from the IoT all the way to the data center back. Also looked at certain aspects more at the chip level, looked at aspects which required a lot of, had a lot of subsystems, like some of these. Looked at more hybrid vehicle kind of designs. So we actually looked at a wide range of applications for this VisualSim Power system. So with this, I want to go ahead and open the floor to any additional questions that people may have.